So hello everyone. It's really good to be invited. I've worked with the Data Science Festival a couple of times before. So at the November Science Festival in London, and it's such a brilliant thing to be involved in. And I always say that AI is for everyone, and this is a real opportunity to kind of, as Dave was saying, build that platform of knowledge. So everyone can get involved because as AI matures and as data science matures as a discipline, it's really, really important that we put our collective minds to the problem. So I'm just toggling through this. It seems to be a bit laggy. There we go. So this is what I'm going to cover today. And as Dave alluded to, this pack is going to be available as a set of resources. I'm going to caveat everything that I'm going to tell you today as this being my opinion and my view and my experience as someone who's been a lifelong technologist. So when I left uni, I went straight into technology, and I've worked in a number of sectors, social impact obviously being my favorite. I did my MSc in computer science and AI, and I've recently completed a course on AI and healthcare models at MIT. So I feel really, really lucky to have got so much kind of industry experience, social impact experience, and academic experience. But you don't need academic experience and you don't need industry experience to get started. So that's hopefully something that I'm going to impart today. And as I say, these are my views. And as you all go on your own respective paths, on your own data science journey, you will have your own opinions that are going to be really, really valuable in terms of building up this knowledge set and sharing knowledge. So this is what I'm going to cover. So I'm going to talk about an AI explanation capability. So if we think about the title of this session, and I kind of feel like I've chosen the longest title possible. I don't know why that is. I should be able to use my words more sparingly, but AI explanation capability is all about explaining the value of your work. So that's a really, really important part of this presentation. And the idea is that as we move through the presentation, we keep going back to this idea of AI explanation capability to make sure that we're always being clear, we're always proving the business case. So we're going to look at the business value case as well. And whilst we talk about value and explanation capability, it's also really important to remember that AI is a superpower, and it's only really our creative limits in terms of where we want to take it. So I want to kind of encourage you to do some creative design thinking. And then we're going to look at building a supervised learning model. So it's a classification problem using genetic algorithms and naive Bayes. So that's some of my favorite models that I've built. I've been using genetic algorithms. So I feel very sort of passionate about this as a model set and an instrument. And so we'll talk through that. So I'm using WEKA today because it can make anybody who can't write any code whatsoever, it can get you started on your machine learning journey. But also in this pack, I've included links to the equivalent Python code so that people can experiment if they don't want to use WEKA. But I'm a big fan, and I'll explain why as we go through. So I'll show you how to build a naive Bayes classifier in WEKA, and then I'm going to talk, going back to that AI explanation capability point, how to be critical, how to be the worst critique of your own work, and perhaps start thinking about doing some model overlay to try and look at different aspects of where an original model might have gone wrong. Again, this is a favourite technique of mine, and it also always shines something new on a problem domain. So looking forward to covering that with you. And then I'll summarise and take any questions. And I'm also going to show you, give details on how you can connect with me and some of my favourite AI things. So if you want to connect with me and talk about those things, or I can share what I've done, what you've done, I'm really happy to connect on those points. So on to the AI explanation capability. And this is something that I kind of thought that I knew in terms of having used kind of predictive analytics, like in an investment banking platform, and also having built many AI models. But actually, if this is one resource that you take away, I've included the link at the bottom. If this is one resource that you take away and use when you're talking about your AI models, it will really do you a favor, because this article is absolutely brilliant, and this piece of learning is so useful. So basically, companies create value through data assets using 5 core monetization techniques. So those are their data assets or data capital. So those might be proprietary assets in terms of data assets that they've generated themselves, or it might be data that they've acquired, or they might have done something new with that data in terms of homogenizing it, bringing it together, or evaluating it as a kind of holistic set. Also data platform in terms of having the capability to interrogate data, having the hardware and software to interrogate data, obviously the in-house talent, and understanding the customer. But this piece of learning is all about the fact that most AI projects still fail. And the reason that they fail is because when you add AI as a strategy to this set of data capabilities, you have to have this thing that's called AIX, which is an explanation capability. So you have to, as an organization, be able to communicate really, really clearly what you're doing with your AI strategy, and you have to justify and explain why you're doing it. There's 4 key things that go wrong or take AI strategies off track, and they're all to do with lack of transparency, complete malleability in terms of results, in terms of you can make results look different depending on how you look at them, and obviously something that thankfully is much kind of higher in terms of ascendancy and significance is this problem of bias, which is particularly problematic in supervised learning problems. So if there's one thing that you read to help you talk about models, read this in terms of how to sell yourself, how to be clear, and how you're mitigating against all of this unclearness, all of this risk of bias. So have a read of that, and I can guarantee that that will help you in terms of your explanation capability to sell your AI strategy. So another key value proposition in terms of you being able to sell what you want to do in terms of a model that you're wanting to build or an AI design that you're wanting to pursue is to think of the value add in terms of belonging to one of these quartiles on this matrix. So obviously, and the good thing I like about this matrix is that you can actually remap this, so you could recast this in terms of looking at social value or social impact rather than this is kind of like a for-profit matrix. But think when you're trying to sell a model that you want to build or a strategy that you want to pursue, you will have to be able to demonstrate how that strategy or that model is going to help support the organization's growth or help increase revenue in terms of as a business strategy. And so if it's not increasing revenue, or if it's or if one of the key parts is cost, have a think about cost, because one of the most amazing values of AI is how you can share scarce resources much more widely by using algorithmic solutions to evaluate problem domains. So reducing costs and improving efficiency are two key kind of other dimensions to sell your model. And obviously, thinking of AI as a superpower, we have to reflect on how we can increase the reliability of product, service, or quality through using AI. So when you come to try and convince someone of a strategy that you want to use, say if you're new to a data science department, or if you're new to a firm, or if you want to sell yourself as kind of being a volunteer who wants to try a particular strategy, consider this matrix and where your model is going to add value, and try and talk around these quartiles in terms of where your model can be a star player. So this is just an example, because I'm not talking about image recognition or computer vision on any level today, but what I like about this slide is the other way to get people to buy in to your strategy is to be super, super clear about the problem that you're solving. And again, if we go back to that idea that AI is a superpower, if we look at the AI frontier in terms of image recognition, so back in between 2014 and 2015, which seems like quite a long while ago now, these AI strategies in terms of image recognition far exceeded human error rate in terms of recognition and classification. So models and graphics such as this are really, really useful in terms of selling your cause in a very, very simple and visual way. So that's the other thing, is to be super, super clear about benefits in terms of fitting in to that quadrant and in terms of your AI explanation. So this is something that I really love about AI, is it really is a superpower. And I think whilst you have to have all of those things in mind about how to sell your proposition to stakeholders, how to have that explanation capability, you have to kind of sell a little bit of that kind of superhuman superpower. And I think design creativity is the dimension that gives you your enthusiasm in terms of looking at a problem set differently, or looking at a model design, or devising a model design. So I really, really like these analogies. At MIT, they use the analogy of Tom Thumb to talk about the ingenuity of their ingestible robot strategy. So they have these tiny swallowable robots that move around your gut and intestine to evaluate different problems or administer different medicines. And I think these kind of analogies really, really bring alive the kind of the superhuman capabilities of AI. And one that I really like that goes with my love of genetic algorithms is Argos. So this mythical person that has 100 eyes, because if you think about how AI is used in a data science perspective to solve and evaluate data sets and data patterns at speed, it is literally this idea of suddenly having capabilities that are way beyond our own human means. So I think thinking about design metaphors is a way to inspire people and bring across your enthusiasm. Right, so every model starts with a data set, and I don't always agree with some of the advice around data sets and their use. I actually think it's more about setting expectations about the problem domain when you start. So if you think about it, not most AI models and most AI strategies are never going to be perfect, but you can learn and you can tinker and you can re-engineer on the way. So it's not necessarily about having the best and the most solid data set to start with, because there's a number of ways you can sell your strategy. So, for example, lots of projects I've worked on, the source of competitive advantage could actually be that the data is a byproduct of the business. So, in essence, the business is generating its own AI monopoly because it's generating proprietary data. So that could be a source of competitive advantage. That data might not be perfect, that data might not be curated, but if it's proprietary, then that is a source of competitive advantage. Longitudinal and curated data sets that are in the public domain, such as the ones I've used here for examples, are very, very good and optimal if you want to go kind of straight into building a model that has some credibility in terms of understanding of the problem domain. And just because data sets are in the public domain doesn't mean to say that you are losing your source of competitive advantage because they're available to everyone. It's actually kind of the reverse, because it's the design strategy for AI models that creates a competitive advantage, not necessarily the data set per se. So I've included some examples of some really well curated data sets, and the advantage of these kind of data sets is that because they're curated, you can prevent that model drift as the data matures away from the model, and you can also prevent some of those biases of representation because they're curated to make sure they're inclusive. Something, because I've got a design background, something that's really important to me is the co-design element of data sets. So to my mind, some of the best data sets are the ones that have been co-designed by the users or the subjects that they represent. It's a very good way of mitigating bias because the data is in essence self-reported, although of course in labeling data there are opportunities for bias to creep in. So a way to mitigate that is to keep mapping back to user case and keep co-design people around you who can explain what the original user case was and how they were supposed to be represented. So co-design is a key feature for many AI strategies. Another great place to look, if you, and it's also good because there's beginner data sets, is on Kaggle. And I like Kaggle because there's also quite mature industry embedded data sets on there. So things around customer churn, telecoms churn, but there's also kind of entry level data sets. And I also like the way that they are totally across discipline in terms of like computer vision problems, classification problems, and they're also very diverse in terms of subject matter. So you can find climate change stuff, you can find kind of information about nutrition and fast food. It's just like really, really diverse. It's a great place to start because it's very interesting. I'm just checking the time to make sure that I keep to my schedule. So once you've got a representation of the problem domain, as in you have a data set, then going back to this AI explanation capability, I always think this is a really good graphic in terms of helping to explain to other people the different potential lenses that you can use in terms of machine learning and deep learning to look at different problem sets. And the thing that I also really love about this graphic, which isn't mine, I've put the attributed it to the author at the bottom, is that it's really, really good for designing model overlay. So if you look at a problem via one branch of this graphic, you can use another branch to superimpose and use another model to really, really test out the credibility of the first thing that you've engineered. And I'm going to talk through an example of this so you can see what I mean. But I think that this graphic is fantastic for kind of plotting your own journey, kind of QAing your own journey in terms of your design journey, and explaining to others the clear path that you've taken. So that's quite a useful one from a design, QA, and explanation capability perspective. So a specific, I'm just going to move my little window because it's in the way of my text. There we go. What I thought we could look at today in terms of imparting some of my learning and in terms of always holding that AI explanation capability in mind is a classification problem. And I think classification problems as a kind of AI starter set or as a business strategy can be incredibly powerful because they're quite easy to understand in terms of the algorithmic activity that's happening in the background. And there's a load of really good industry examples of how they've been used to bring about competitive advantage in the public domain. So they're not difficult to sell, and you can be really, really imaginative on how you use them or how you apply them as well. So classification problems, if we think back to the branch graphic that we looked at in the slide before, classification problems deal with predicting a set membership for a data instance by learning from existing data about a problem domain. So basically, you use data that describes a problem domain or describes, so for example, an existing data set where historically, say, customer churn has happened. So you have this big set of data that includes all of these customers and different data attributes, and whether they've churned, as in left you or stayed with you or not. And then you use that to train a model. So it's a classification model that you can use on new data. So you can find out, for example, whether new customers are going to leave based, or existing customers who are still with you are going to leave based on those attributes pattern. And if you think about how that classification algorithm works in terms of its predictive ability to tell you whether something belongs to a certain class or not, you can start seeing all of the different ways that you can that you can deploy a classification problem to support decision making or solve a problem. So it's a supervised learning problem, and its strength in terms of how well it's going to work or not is mostly, well, actually, it's pretty much all down to how well the problem domain in terms of your data set is understood. So it's really important to spend time on the data set, making sure that all of the features are labeled so that you understand exactly what those features mean, because it's those features that determine whether that instance is going to be predicted to belong to a yes or no set or not. Labeling data brings with it its own problems. like bias, which we will continue to talk about through this session, because labeling data is mostly a human activity. And obviously all of us humans approach problems with our own set of subjective beliefs. And so that's how we can transfer bias into a data set. But I'll talk more about the model overlay side as a potential mitigation against that. So I've included the link to the Python code, and I'm going to show you how this works in WEKA. But this is the basic kind of algorithmic activity that you need to get your head round to understand what's happening with a classification problem, and being able to explain it in such a way that other people kind of have belief in what you're doing. So basically, it's a probabilistic, so we're talking about naive Bayes particularly as a classification mechanism, so that decides whether something is a yes or no in terms of whether that data instance should belong to a particular set. So for example, is the customer going to leave, yes or no? Is this a dog or is this a cat, based on these attributes? So it's a binary yes or no predictive algorithm. And so the way that it works is it takes one instance, so think of that instance as X, and then it looks across all of the attributes, although it actually does this independently. So think of those attributes as column values, like X1, X2, Xn, as in the length of your spreadsheet. And it looks across all of those and determines, basically from its training knowledge on prior data sets, whether that instance should belong to a certain class or not. So is that instance, say you're talking about a customer, is that customer going to leave your business or not? And if you find this difficult to visualize, the way I always think about this is that if you think of like a Python data frame or an Excel table and visualize the X matrix as simply the values in your columns in your Excel spreadsheet, and think of X obviously as your data instance. That might be a customer, or it might be, it could be absolutely anything depending on what your problem set is. And just think about, really, it's this algorithm that looks across all of those different variables, as in X1, X2, to make a decision, a predictive decision about whether that instance is going to belong to a certain class or not. So I think that's by looking at the data set through that lens, I think it's an easy way to visualize what's actually happening with the kind of algorithmic behavior in terms of the X matrix. So why naive Bayes can be a good choice? Now, I think not only because it's quite accessible in terms of that kind of beginner and entry level, there's a number of reasons it can be a good choice. So it's used very widely in industry, and particularly in telecoms industry and kind of high fast customer movement industry, where customers can move very quickly to substitute products or substitute services. And I always think it's when you're learning or when you're applying a new model on a unique problem set, it's really, really good if you can find lots of information in the knowledge domain to support you. So that's one good reason why it's quite an interesting one to look at. Also, naive Bayes works quite well on small data sets, so you can prove a concept. So going back to that point about AI explainability, you can use a relatively small data set to show its value as a decision support making tool. So you're not constrained by having the largest data set as a data asset. And something else that I think that it's really good for, some things that I've learned on my journey, is that it's really good as well because of the confusion matrix output, and the way you can tinker with it to get different results. It's really, really good for exposing some of those AI cancers like bias. So, and the Python code is there via that link at the bottom. So I think this is a good one to look at, and one that I think is quite flexible in applying to different problem domains. And of course, these are just my views. So there to support your learning and kind of, you know, your design thinking too. So another reason that I like Naive Bayes is because I think you can really boost its performance, boost its accuracy by using the wonderful thing called the genetic algorithms. There's a number of genetic algorithms available open source, and they're also available as part of the WEKA toolset, which I shall talk you through shortly. The reason that I like them so much is this idea again of an AI superpower. So they can quickly, provided it's the right algorithm, they can quickly assimilate very large data sets and can look for all the hidden patterns between the data, and they can reproduce the best candidates in terms of your instance variables that you can use to train your classifier. So you can get much, much better results in some circumstances by using a genetic algorithm before you train your naive Bayes classifier. So I love these, and I've seen them work really, really well in lots of different cases. They provide insights that as humans that we would never ever be able to see, and as like many AI superpowers, they're inspired from nature, where in genetics the fittest pieces of an animal or a plant are used in the reproductive process or mutated to produce a better or stronger or more robust version of that animal or plant. So they can be very, very complex if you look into kind of what's actually happening in terms of some of the mutation and crossover. But if you just think about them as something that is a heuristic, as in it's optimizing your search space, giving you more clues about how to train your classifier, which pieces of the data provide the biggest kind of support for your classifier model, then you're able to explain that in a way that adds value. So I'll now get on to WEKA. I'm always worried that I'm not actually saying this right, but so WEKA is an open source application that has its own graphical user interface. So you can become a machine learner or an AI model strategist without writing any code at all. And I think that's incredibly powerful in terms of thinking about this idea that AI is for all. And I also think it's really useful in terms of comparing different models. So as in looking for weak points in, say, like a scikit model, or weak points in another architecture. And it's really, really good from a learning point of view because you can master the properties of all of the different algorithms it offers. And it's really, really good in terms of that early analysis of your data set, because you can view all the different bins. You can look at things like class representation, and the visual graphics aren't anywhere near as good as what you can get in Python using like NumPy or Seaborn, but in terms of a way in to mastering the kind of the maths and the computer algorithmic activity, I think it's absolutely fantastic. So it was designed to use with Java, but it's now also available as a Python wrapper. And in my opinion, again, this is just my opinion, I think as soon as Python make a wrapper so you can access another API, you know it's something that's good. So and to prove this point, I actually did my my AI MSc independent research project using only WEKA, because I wanted to prove that you can build a really robust AI model and data science project without having to be a wizard in coding. And I think it's really, really important that when we look at AI and applying AI, that we don't get all oh, this is just for that type of person, or this is just for this type of person. AI is for everyone. We've all got something to contribute. So massive fan of WEKA, but that's just my opinion. So I've included on these slides how you can download it. It's free. So the current version is 3.86. Another great thing about WEKA is that you've got a really big body of users. So there's a really great group kind of chat. So you know how you have Stack Flow in Java, but you have kind of like a group chat all around WEKA who've kind of solved other problems and can help point you in the right direction. And what I'm showing you today is all done via this Explorer button on the WEKA GUI. So you can literally download this in seconds. You can go to Kaggle and get yourself a data set, or you can go to Scikit and get Scikit and get a data set, and you can get started as a machine learner. And remember, it's all about design, not about coding ability. So I think I've probably got so enthusiastic, I've probably said all of these things, but I'll cover them briefly. But if we go back to that quadrant in terms of how to selling a AI strategy, think about the cost benefit, because WEKA can be completely programmer language agnostic. So you don't need to tie an AI strategy to a particular coding skill set or a particular talent asset, because WEKA transcends coding language, because you can call the algorithms from within the GUI. So I've talked about visualization. It's very good for kind of doing that first and early analysis on your data sets. It automatically creates holdout sets. So it divides your data set into folds and then averages out the behavior across those sets. So it's very explainable, and it's very reproducible. I think the downside is some of the output graphics around perhaps the clustering side. You can do way better in Python, but you still get the idea, and you can obviously you choose your path. So these are the steps to how to build and develop a naive Bayes supervised learning classification problem in WEKA. So I'm actually just going to quickly talk you through the GUI here. So first of all, once you've looked at your data, you go to the genetic search, and the genetic search looks at your data set and selects the attributes that should be used to train your naive Bayes classifier, because these attributes are the highest quality ones, guided by that heuristic, which provide the best knowledge in terms of the quality of that data in terms of guiding the classification model. And then you literally just switch between tabs to go to the Classify tab and choose Naive Bayes, and then Naive Bayes will classify that data set to predict whether that instance should belong to a certain class or not, as in, so if it's a customer, is that customer going to leave? Yes, no. If it's likelihood of developing a disease, say, will this person develop this disease? Yes, no. And the classifier lists out all of the instances that it predicts as yes, as in it belongs, yes, it belongs to that set. All of the instances that it identifies as belonging to no, like no, that behavior will not happen, that data instance will not belong to that set. And you can also get a really, really good idea about how well your data is labeled by looking at the confusion matrix at the bottom and looking at your false positives and false negatives. So it's a real insight in terms of looking at the quality and the reliability of your model. Going back to that point about AI explainability and going back to that point about selling the value of your approach, this is where the model overlay side comes in. I'm going to use WEKA for this as well to show you how you can do this. But remember when we looked at the ML deep learning branches in terms of the different AI strategies that belong to either supervised or unsupervised learning. There's lots of different tools that you can use. So the biggest thing that I would say in terms of any AI model building activity is never be afraid to put your results under scrutiny. The worst thing you can do, and I used to do this, because I was scared of getting into trouble when I had my early days at Credit Suisse, about any data problem is pretending that you are really confident about your results, pretending that you have got like a magic panacea, when actually it can often be just as important if you disprove an approach or if you identify the weaknesses in the approach, because by doing that, you can make the model better. And by doing that, you can be an AI project that doesn't fail because you've actually addressed the weaknesses and flaws in the model head on, and you've worked out a path on how you might mitigate those. And this is especially true with supervised learning, because remember, with supervised learning, your problem data set has likely been labeled via human intervention, and with human intervention comes bias. So never be afraid to be the one in the room to call out a weakness, a flaw, a possible risk of bias. So that is a strength and not a weakness. So now I'm going to talk about model overlay. So in terms of a classification model like Naive Bayes that we've looked at, a really good way of being self-critical and thinking, I've looked at that confusion matrix and those numbers look really good. So that set of people or that set of data, data instances have been classified as X, as in they've been classified as belonging to a particular class. But how accurate is that? Or is that supervised learning? Is that data set labeling? Is that actually off? And so what I think WEKA also does really well is this model overlay thing, where you can revisit your original problem, as in your classification problem, and use supervised learning, an unsupervised learning technique to really, really be critical and check the validity of your model. So clustering is a branch of unsupervised learning, and I'll talk a bit through that now. So unsupervised learning algorithms are great, and they tend to be used in separately from supervised learning problems because they're kind of used to look at different outcomes. So unsupervised learning is often used to decide whether a data instance with its attributes is what it might have in common, so it belongs to a certain set. So the famous example is whether a plant is an iris based on its petal length, leaf length, and stem length. So it classifies all the different instances into clusters. So like things are clustered with other like things. So you can see how many different parts there are to a data set. So you can see that, say, for example, you're looking for dogs, cats, and rabbits. A k-means clustering would cluster all the data that looked like a rabbit in one cluster, and then all the data that looked like a dog in another cluster, and would add all your data points so you can see what no knowledge of the domain, what the unsupervised learning algorithm might make of your problem set. And there's the Python code for how to do that there. So basically, a cluster aggregates data together because it shares certain similarities. So on this image, you've got two different things. So say one's dogs, one's cats, and with no knowledge of the problem domain, the algorithm looks at those data points and say, these instances belong to this family and those instances belong to that family. So it's a way of looking with no predisposition, no subjectivity, no bias at what things might be in terms of their identification. And so you can do this by, so this is on the same data set using simple k-means through WEKA. And on this data set, I got 3 different clusters, which told me some interesting things. So there's 3 kind of areas of core commonality in that data. So 3 sets of collective behaviors. And this is really, really interesting. As I said, the graphics in WEKA aren't great, but what I want to show you about this overlay is that here under that one in that red circle, those are data instances where the naive Bayes classifier said that they belonged to a yes set, but actually all of those little red crosses in that mass of data points actually exhibit behaviors which suggest that they do not belong to that classification. So by doing that model overlay, you can really stress test your results and your assumptions. You can go back to the data, you can go back to your co-design group, and you can start improving on that journey. I'm just realizing that I'm tight for time, so I'm going to move to the summary. So to summarize, approach every model build from this AI explanation capability. The more you understand, the clearer that you can explain it to stakeholders, the more buy-in you get, the more likelihood that you'll succeed. Remember that AI is a superpower. Be bold, be imaginative, as long as you can explain it. Map every model to the business quadrant to prove that you're adding value, prove that there's a business case, prove that there's benefits. And remember that successful models are about considered design decisions, including co-design. Co-design is super important, and learning and re-engineering from failures. It's nothing about being a code wizard, in my opinion. And so these are my AI interests and how to connect with me if you want to talk about any of these or explore any of these. So as you probably guessed, I love using WEKA. I love Python, especially the data visualization and scikit, learning side of Python. I'm building some stuff with TensorFlow in terms of language analysis, ChatGPT, sentiment analysis and social impact. And so feel free to connect with me. My details are there, and handing back to you, Dave.